So section 6 is all dealing with the valence shell electron pair repulsion and what shapes molecules will form and what types of bonds different atoms will form when they join together. So part 1 says outline the principles of the valence shell electron pair repulsion theory, and basically what that is that electron clouds, we'll do EC here, make sure to write things out completely, but this is what we use during class. Electron clouds will repel one another as much as possible until they start interacting with other electron clouds and form predictable shapes. And just in case you can't remember, electron clouds are either unpaired or unbonded, we'll say unbonded electron pairs, or a single bond, or a double bond, or a triple bond. Okay, part 2 of this question, gotta love that they have so many different parts. It says use the VSEPR theory to deduce the shape of H3O plus and C2H4. So we're looking for two different ones, H3O plus and C2H4. And then for each species, in doing the predicting the shape, we need to draw the Lewis structure, which it's good that they have that as part of this, because without a Lewis structure it would be difficult to identify. We'll name this shape and then state the value of the bond angles. There's a lot of memorizing in this section. First of all, whenever we want to attack these Lewis structure, we want to see what number of valence electrons each of our atoms have. So we have hydrogen here. There are 3 hydrogens, and each hydrogen has 1 valence electron for a total of 3 electrons. Each oxygen has 6 electrons. There's only 1 of them, so there's a 6 there. And that 1 plus means that we have lost an electron, which means we're going to have 1 less electron total. So 6 plus 3 minus 1, that gives me a total of 8. So this is always my check at the end, make sure that I have 8 electrons total, that I match my total here. I'm going to put oxygen in the middle because that's the one that needs the most. I'm going to put my 3 hydrogens around it. Each of the hydrogens are satisfied with each of these single bonds because that means it's getting the effect of 2 electrons. Hydrogen can't hold any more than that because its first energy level is so small and so close to the nucleus that it can't hold more electrons. The oxygen is not satisfied right now. It has 2, 4, 6, but I'll put in 2 more. And that'll be good because now I have 8 total. So I match my total. I meet the octet rule, so check octet. So that part is good. And then I can look here. I have 1, 2, 3, 4 electron clouds. Whenever I have 4 electron clouds, but only 3 of them are bonds, it means that I have a trigonal pyramid shape. And the bond angles are right around 105. Okay, the next one, C2H4. I'll start out with the same thing, do some counting. So I have 2 carbons, and each of those carbons have 4, so I'm going to have 8 electrons there. I have 4 hydrogens, so 4 times 1, there's another 4, so I'm going to have a total of 12. No charges here to worry about. So I'll put my 2 carbons in a row and put a hydrogen, 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 hydrogen. And I can see that I've got 2, 4, 6, 8, 10. That's not enough electrons. My hydrogens are good. They each have 2, 2, 2, 2. The carbons are not good. If I put unbonded electron pairs around, then I'd have 2, 4, 6, 8, 10, 12, 14. That is not good for us. That's more than what I need. So I'm going to put in a double bond. Now the carbons each feel 2, 4, 6, 8, 2, 4, 6, 8. So my octet has been checked. Now I need to check my total. 2, 4, 6, 8, 10, 12. And I am good. Okay, we'll pick one of our carbons to look at. So we'll pick this one, and it has 1, 2, 3. So very roughly, and I say roughly because this part is so much bigger than the rest of the other 2 hydrogens that are bonded to the carbon, that it's going to be a rough estimate here. We have 3 electron clouds. All 3 are bonds. That means we should have roughly a trigonal planar shape. Which is going to be about 120 degrees. Now again, I'm going to say about because this is going to take up so much more space than the other 2 electron clouds that it's going to push them more towards one another, so the hydrogens will be closer to one another, and there will be more space away from this big group here. But that's roughly going to be our answer. Then it asks us to predict whether they're going to be polar or not. So it's part 3. But it's asking us anyways. Whenever you see an unbonded pair, an electron cloud, an unbonded pair of electrons, that's going to be polar. So H3O plus is going to be polar due to unbonded electrons. The C2H4, on the other hand, is going to all cancel each other out. If we were to take this and bisect it either way, it's the same stuff on either side, so even though there's an electronegativity difference between the carbons and the hydrogens, it's going to cancel out. So C2H4, nonpolar, due to shape. Then it says for part 4, use the data table in the data booklet to predict whether the OH bond or the ON bond or the NH bond would be the most polar of the bonds. And so what we would do is look up each of these numbers and find the difference between them, so subtract. Once we find that difference, we're going to identify which one has the greatest difference, and the greatest difference would be the most polar. It should end up being the ON bond, without looking at my data table. You can double check that. Just make sure the greatest difference is the most polar. Part B says that we need to predict and explain which of the following consist of molecules. When they say molecules, they're looking for electronegativity differences that are going to be between 0 and 2.0. Because 2.0, if we remember, of the electronegativity differences makes it ionic. So if we look at these different ones, NaCl is going to be ionic, so that does not consist of molecules. BF3 we could calculate out. My guess is it would be. The electronegativity difference should make it a polar covalent molecule, so between 0 and 2.0. CaCl2, big electronegativity difference there. It would not be considered a molecule. Na2O, or N2O, excuse me, N2O should be a polar covalent molecule. P4O6 should also be a polar covalent molecule due to the electronegativity difference. FES, I would be inclined to say ionic, but again, you'd want to check those data table packet to verify that the electronegativity difference is great enough. And then finally, CBr4 would be polar covalent. Part C asks us about diamond, graphite, and C60 fullerenes because they are all allotropes of one another, which means they are made of the same thing, but they have a different shape. So it says first to describe the structure of each of the allotropes. The diamond, we've got a very strong tetrahedral shape. The graphite, we've got rings held together in two-dimensional planes, making it three-dimensional. And the C60 fullerenes, those are mostly our buckyballs and our bucky tubes, and so we are spherical in shape and also very strong. Part 2, we're going to compare the bonding in diamond and graphite. Diamond is very strong. Graphite, the layers are held by intermolecular forces, not by actual bonds. So as we're going from layer to layer, that's actually quite weak. Within a layer, there's some strong bonds there. Those aren't breaking up when we use our graphite pencils, but from layer to layer, that's how we can lay down that nice layer of